Okay,
Yes,
good.
it works.
Okay, cool.
Thank you, James.
I'll get back to my class. I talk to you guys later.
Okay, thanks. See you later.
Yeah, see you.
See you. Okay, so hi everyone. So today we are going to do some practical exercises for Fermi data analysis. So I promised some. Yeah, last time it was theory, so today it's gonna be like exercise session. So I decided that I can just share my screen and show you things, because I'm not sure that everyone will be able to smoothly install the analysis tools, and yeah, it will take some time, but maybe sometime later. So it will be easier because I have everything installed, and I worked with this package for some time already. So I guess I can just share my screen, and yeah, it will be good enough. Cool. So let me do that. Okay, you should see my screen now. And so yeah, we will be going through a bin likelihood tutorial. So last time I was showing, maybe I will open up the notes again. Yes. Lectures. Yes, so last time I was going through the theory of the analysis, so likelihood analysis. So just to remind, so yeah, here we compute the source flux as a result of the optimization. So we have a model, we have to generate a model and then adapt the model parameters so that the data is most likely to be generated from this specific model. And so yeah, so this was step-by-step tutorial. I imagine it will be quite tedious, especially without really showing stuff. So the first, as I said, so we can start and really do some exercise, and we will be focusing on a blazar. So it's an AGN with the jet directed towards the observer, and we can try to analyze some data. So first we need to download the data, and yes, so we will be focusing on this source. So this is called Markarian 501. So this is a blazar, and it is flaring from time to time. So it shows an increase of flux all over the energy spectrum from radio to gamma rays. And in fact, these flares can be varying, like the variability can be proceeding at very different time scales, ranging from as short as minutes and as long as months or years, or yeah, as long as that. So I decided to check out the data set during June 2012. So this is a paper on this source, Markarian 501, so modeling paper. And so yeah, so they present flaring history of this source, and in general this source has a very hard spectrum, meaning that there are lots of photons at high energies. Like the more hard spectrum is, so you have more photons at very high energies. And so during flaring activity during June 2012, this source showed extreme behavior. So it was reported that, okay, the paper is 2020. So up to 2020, this was the hardest spectrum observed from this source. So the highest amount of high energy photons, and it was behaving like extreme HBL. So the spectrum stretching up to 10 TeV. So that's why I am curious to also, so this is in very high energy. So this is in TV domain obtained with Cherenkov telescopes, but it would be interesting to complete the spectral energy distribution with Fermi data in lower energy domain, so somewhere here to complement it, and then we can have more information on the source and see how it behaves. So yeah, it's just an example of the data set I selected. So probably someone did that, but for the sake of the exercise, we find so just some interesting data set to play with. So we need to download the data first. So yeah, so the activity you see from March to July 2012, and the highest activity was around June 9. So I think we can just download the entire month of June of data for this source. So June 2012, and the source is named Markarian 501. So this is the Fermi Gamma Ray Space Telescope website on NASA platform. So I think there are links in the slides. Yes, so fetch the Fermi-LAT data. So if you click here, you get to this page where you can download the data. So this is the very first step. You need to get the data. So you type here Markarian 501. So these were the, okay, I was downloading previously other data, so it was giving me hints. So okay, coordinate system, we keep the standard one. Search radius, okay, standard one will be 10 degrees. So it's a point source, and we selected 10-degree region of interest. So to remind, so region of interest is the like certain field of view around your source, because you can have other sources which can interfere with your source, especially at low energies where angular resolution is poor. So observational dates. So yeah, you can indicate it with 3 systems. So Gregorian, MET, and MGD. So MET is the mission elapsed time. So time in seconds that elapsed since the launch of Fermi in 2008, June 11, I think. So I prefer MGD. So MGD is modified Julian date. So probably you're familiar with, and you can actually find the MGD, so you can convert the regular date, like we need from 1st June to 1st July 2012. So you can convert that to MGD using just MGD converter. So just go to Google and type MGD to date converter, any first best online converter. So why not this one? So this converts from MGD, and then we need to convert from, you see, from regular date to MGD. So we type here 1st June 2012, and then we get our modified Julian day. We just copy that. Okay, where we are. Okay. Yes, so this will be the first one. And okay, I already did that before. So yesterday I was playing with the data, and so I guess we can close it. So if you do that for the next month, so plus 30 days, okay, you will get this. So you specify these dates with a comma. So start, comma, and date. So this is 1st June, and this is 1st July, 2012. So where the source was showing some interesting activity. Then the energy range in MEV. So you want to specify the energy range in which you want to analyze your source. So I recommend, so for the highest quality of data, so from 100 MeV, and the photons during 1 month, you don't have enough statistics to go up to the very highest threshold. So this source, Markarian 501, is one of the, in fact, one of the brightest gamma ray sources in the sky. So that's one of the reasons as well why I selected it. So bright source, far from the galactic plane, so there wouldn't be a lot of background noise. And also there is interesting behavior. So you can go up to 100 GeV, so it will be 100,000 MeV. So beyond that value, you will have too few photons. And to get to, in principle, so with Fermi-LAT, you can go up to 1 TeV, but you need really statistics, a lot of statistics. So meaning stacking data, observational time for this. So I was analyzing CREB data some years ago, and I stacked 10 years of CREB data, and you can really reach 1 TeV, but this is, again, this is the brightest source on the gamma ray sky. So you need really 10 years of exposure to reach 1 TeV. So here for 1 month of observation, we won't get any close to that. So 100 GeV generally is typical upper limit. So 100 MeV and 100 GeV. So you select photon data, and you need spacecraft file. So spacecraft file reminding. So this is the spacecraft file contains the information about the orientation of the spacecraft and the different auxiliary information needed for analysis. So all we need to do is press start search. So query submitted. So we have to wait a bit, and then the results of the query. So and download of the data can be found here using the link. So we can click the link. So query complete. So we can just download the data. So we can simply use wget to do this. So we copy this and open the command line and just paste here. So I already downloaded the data, so I won't do this again because we will not be waiting for the download. So I will simply go to the folder where I have this data already. So we have here different files. So yes, these are the files. Sorry, it's highlighting maybe. Yes, so these are the files. So SC is the spacecraft file, PH is the photon, so gamma ray photons. So we are curious, so what's inside, right? What's inside these files, and we can open them. So these files are coded in FITS format. So to open them, you need FITS viewer. So FITS viewer, FV, and then we can specify the name of the file, so spacecraft or photon. So let's open up the photon file and see what's inside. So yes, so it's a very simple software. As you can see, nothing fancy, just the most basic. And we see that this file contains 2 branches, so events and GTI, so events and good time intervals. So events, you can see there are 100,000 of events. So for our selection criteria, so from 100 MeV to 100 GeV, and during 1 month of observation in June 2012 for this source. And we can open up header. So this will show us the description of this branch, all the columns, and all will load the data itself. So this is how the data looks like. We have to wait. Okay, it's a very large file. Okay, now it's good. And the header explains all these columns. So you can see here, so these are all events and the data about these events. So first column, so each of these lines is 1 count. So 1 count is detected by the Fermi-LAT during the observation of the source. So you have energy in MeV. So 100 MeV, 164, blah, blah. Then you have the arrival direction specified by 2 coordinates. So Ra and Dec. So from where on the sky this arrives. So this will be within this 10 degree radius, which we specified. So 10-degree circle around the source. and then galactic coordinates, then theta. Okay, what is theta, what is phi? So we can check here in header. So theta, so inclination angle of event in instrument coordinates. So this is the angle between the axis, the z-axis of the detector. So it's like a cube. So it's basically cube 1 meter by 1 meter by 1 meter, and so it's arrival direction of the event with respect to the z-axis. So then zenith angle, okay, and various other information. So time, so when it arrived, event ID, and other information. So this information will be needed for filtering. So we will be selecting events with high probability of being gamma rays, etc., etc. And okay, so this is how it looks like. So there are 100,000 of events here. So yes, you can see a lot of information to deal with. Then let's open up the spacecraft file and see what's inside the spacecraft file. So this is the second one. Okay, it was named SC, and okay, let's see inside. Okay, so yeah, there is a header with the description. So any FITS file you can open up in the viewer and just see the content. I don't know if you ever work with FITS files, so, but yeah, this is the, why is it not? Yes. So yeah, this is typically how it looks like. So we open up the spacecraft file, and the information here is the following one. So as I said, it's containing information about the orientation and position of the spacecraft, various other, we will go through these quickly now. So the header describes you the, why I cannot move it? Yes. So the header contains information about the columns. So what is this? What is this? So this is the information about the spacecraft during the period we are interested in, during June 2012. So start and stop. So the information about the spacecraft is provided over 30-second intervals. So the sampling is 30 seconds. So at each 30-second interval, the information is updated. So this is the start of the interval, and this is the end. So the end is always start plus 30 seconds. And so this is the time interval. And so this is the latitude and longitude in Earth system. So you can find here, so ground point latitude, ground point longitude. So the position of the spacecraft. Then rad geo. What is rad geo? So you check here. So this is the spacecraft altitude. Then Ra zenith, dex zenith. So everything is here. Ra of zenith direction at start. So various other information. Important one also, this in SAA. So this is whether the spacecraft was in South Atlantic anomaly. So the date when, so South Atlantic anomaly is where the radiation belts of Earth are the closest to the surface, so that you have higher degree of high energy particles penetrating through the atmosphere. And if the spacecraft is passing through the zone, it's exposed to higher number of charged particles, and so the data will, so it might affect its operation or just contaminate the data. So you want to avoid the data that was collected when the spacecraft was passing through the South Atlantic anomaly. So it is, so whether the spacecraft was in it is coded with this phrase, or let's say marker. So in anomaly, so F means false, means it wasn't there during this time. So yeah, you see it's all the time, it's okay, but we will filter on that during the data selection. Then Yes. Okay. Many other different information, lifetime, and so this all information about the spacecraft operation will be needed when we will filter the data. So this is the content of the data. Okay, of the data files we downloaded. So we will proceed with analyzing that now. If you have any questions, it's a good time to ask. Okay, no questions. It seems like. Okay, yeah, let me open up. Okay. Okay. Okay, I cannot access the chat by some reason. So anyway, if you have questions, just don't hesitate to speak up, and I will try to reply. Sorry, I cannot see the chat, so just be aware. Yeah, just ask it out loud. So okay, so now we can start with analyzing that. So we want to what's the goal? So we want to see what's the spectrum of the source. So as I said, the period which I selected for the source is when it was showing the most hard spectrum. So very interesting behavior, a lot of photons at high energies. So we want to see the spectral shape, the behavior. So we will be averaging. We want to accumulate enough statistics. We want averaging for the entire month, and then probably we want to bin in shorter intervals if the statistics will be allowing that. And so let us start with doing the analysis. Yes. So the first step. Is to select the data. So filter the data, select the events. So this was the slide, the step 3. So using the tool GT select. So all right, yes, for that we need Fermi Tools. And where do you get it? Just quickly. So now Fermi Tools is, well, you can install it with Conda. And to do that, so previous you have to download package, install it. Now it's simpler. So now Fermi is integrated into Conda, and all you need to do to install is just to run this command. Yes, you have to install, if you don't have Conda package, you have to install and update Conda. So this command will install the necessary packages for Fermitools to function, as well as the Fermitools and auxiliary information, auxiliary data, and then you can run these tools using, you have to activate the environment. So in order to invoke the different tools, GT select and others, you need to enter this environment, otherwise the shell will not understand you. So you need to run these conda activate Fermi. So let's do this. Where is my, yes. So conda activate Fermi. Okay, it is complaining about, okay, there are some warnings, but it will function normally. I have to update a couple of packages. So, but it's gonna function normally. So now you see we are in the Fermi environment. So you can see here Fermi. So now the shell will understand the commands which I use to invoke the tools, and we can proceed to analysis. So we have to make selection of events, like good data from the entire data set, from all that list of events. So events only from the source region, right? From the energy time range of interest. Okay, this was already done, and we won't really narrow the time range or energy range. We want to do binning at this point. So we want to produce spectrum. So we want to select events in energy bins. So I will use 3 energy bins. So as I said, I selected events from 100 MeV to 100 GeV. So let's make bins with one energy bin, 1 decade. So from 100 MeV to 1 GeV, 1 GeV, 10 GeV, and 10 GeV, 100 GeV. So these will be wide enough to accumulate enough events. So again, events only with high probability of being gamma rays, and we cut on events types. So standard cuts and apply zenith cut. So we can run it. So let's check again. So we have our files. And okay, I already done the analysis, but we can, rerun it. It's fine, it won't take long. So first okay, let's do like this. Okay, maybe I can, yep. Okay, it's working, okay. Yes, so we are at this step at the moment. So we want to do selection. So we need to, okay, why? Okay, yes. So we're in the environment of Fermi, and we can call the tool which is doing the selection. So it's part of Fermi Tools, GT select. And we need to specify the different information. So we run GT select. Okay. Yes. So, and it is asking for some input. So we need to specify the input photon file. So this will be this file, right? So we specify this file. Then it wants you to name the output file. So what will be the file containing the filtered events? So I already done that, but let's rename it a bit so that we will have two in parallel. So as I said, we want to apply binning, so 3 bins. So we will do, in fact, we can write a script which will do it iteratively, but okay, we can do, it won't harm, we will have only 3 bins, so we can do it manually. So for the moment, I'm selecting the data for the first bin. So from 100 MeV to 1 GeV. So I call it bin 1. And as I already have run things, I will duplicate and I have to add, I don't know, maybe prefix version 2 or something like this. Yeah, maybe here version 2, doesn't matter. So because I don't want to rerun again, but I just want to duplicate. So the output file, so the idea is that this is filtered data, so Markarian 501. So version 2 binned, as I'm binning in energy, filtered as I apply cuts, and then the first energy bin. Okay, so then if I want to cut on the region, so if I want to select new circle, if I want to select, for instance, events from the specific position on the sky, but I don't want to do that, so I specify indefined. So if I don't want to do cut on the specific parameter, so I have to type indefined. So you see, it's a command line interface. So the tool is asking you for information, you providing the information, and then you have the output file. So you can script that. So you can type GT select and in file equal to. So in fact, it's in real analysis, you don't have to do that manually. So, but okay, for the sake of this exercise, we will do it all like this. So again, we don't want to do any cut. And for radius, again, we keep the region as it was. So 10-degree circle around the source. So we don't apply any cut. So again, for the time binning, if we want to produce light curve, at this point, we want to specify the starting time and ending time. So we want to apply binning in time. But since we're interested in spectrum averaged over the entire period, So we won't do any cut on time, so we won't select a specific interval. So again, we type indefined, so it will be the same time interval as was before. Same for in time, so we will keep it the time interval as we selected, so for the entire June. Now we can start doing our binning. So you remember, so we had a wide interval of energy from 100 MeV to 100 GeV. So here the first bin will be from 100 MeV, and upper limit will be 1000 MeV, so 1 GeV. So 1 decade wide bins. And I apply cut on zenith angle 90 degrees to remove contribution from the limb, earth limb, so which is source of background gamma rays. So it has run the selection, so we can check. So the file, the filtered file is this one, so Markarian file 1 version 2 bin filtered. So this is these are filtered good events in the energy range from 100 MeV to 1 GeV. So let's open up and see what's going on. So we can check the content. So you have now here, so you remember there was 100,000 events, and only in the energy range from 100 MeV to 1 GeV, you have only 4,600 events. So it was drastically reduced. As you can see, there are very few events remaining. So the filtering was done. And again, you can open up and see, okay, it's just the same, but the events were filtered. So we have now fewer events. Okay, so yeah, these is the list of good events. So the events filtered according to the criteria that we applied during the selection. So you redo the same for in fact for 2 other bins. So you type gt select, then you specify your files, but you name files bin 2, and then here you specify 1000 and then 10,000. So this will be the same for second bin, and then for a third bin it will be 10,000 and 100,000, and then you will have. So in fact, I have already run that. So these are files which I obtained. So bin 1, so bin filtered events for bin 2, bin 3. So if you open up bin 3, for instance, so you will see only, I think, 24 or 25 events. So it's at high energies. So this bin 3 is from 10 GeV to 100 GeV, so the highest energy. So we have very few photons. So we have 24 photons. So these are the events which are satisfying the selection criteria, our cuts at very high energy from 10 to 100 GeV. So yes, so we have reduced number of events. So the selection is now done. So you have output files. These are the output files. Sorry, I lost track where they are. Cool. Yes, bin filtered. Then next we have to select good time intervals. So you remember we were opening a spacecraft file and there were different informations, including South Atlantic anomaly. So we want to filter out all the events which were collected when the spacecraft was operating not properly. So when this information is taken from the spacecraft file, so this is a bit different from the GT select. So we are filtering events based on the specific criteria, based on specific properties of the events themselves. But here we are filtering the events based on the operational mode of the spacecraft, so which is a bit different. So these are 2 steps a bit separated, that's why. And so we run these command GT MK time. So just as a reminder, so all these steps are listed here. So on the tutorial, so this page which I share with you. So, and the examples how to run these commands. So for GT select, so yes, so you have to follow, if you want to repeat that, you have to follow exactly what's written here. So okay, I think I missed, yes, I think I missed to specify these ones because these are not explicitly asked. Yes, I'm sorry, because the cuts on event class and event type, these are in fact hidden parameters, so they are not asked when you run the command, so you have to specify immediately. So okay, I did that when I was running the analysis yesterday, but for the sake of the exercise, okay, I will repeat it correctly. So yes, sorry, so we can repeat this for the second bin. Yes, I'm sorry, I forgot about these hidden parameters, so we have to run these because I ran just GT select and then I didn't apply any cut on. So this means that we want to select only the events with high probability of being gamma rays. So I mentioned that in fact when the cosmic rays can be misclassified, so there is a rejection shield, but in fact these events sometimes they can still induce showers, and we need to filter out because based on the spatial extent of the shower we can distinguish between charged particles and gamma rays, but not always. So there is no strict transition, so we need to filter out events which are suspicious of being not gamma rays. So now I will rerun quickly this command to just, you know, that you have the idea of how it's done properly. So GT select event class 128, event type 3. So this is selecting the conversions, so from front and back. So we want to have more statistics. So you don't have to think probably too much about that. So you just do the standard thing. So this is the standard analysis values. So this is how, and then you run, okay, this is the input file. So it's suggesting you, if it's the one you want, then you can just not repeatedly enter it. So you can just press enter and it will be, so you see, so output file. So the same name. So again, okay, because it remembers the values, so we just rerun it. Yes, so it just overwrote this file that was created just before. So the version 2. Yes, so I just reran it with this because it's very important that we select really events which are resembling to gamma rays. Then we return back to normal. So we run the GT MK time. So we want to select intervals when the spacecraft was operating normally. So again, everything is in the tutorial. So you just run GT MK time and specify the spacecraft file, the filter expression, which is this one is the standard one. So basically it says that the spacecraft was operating in usual regime. Then okay, apply. So here in this tutorial, this is the standard analysis values, so we have to use them because we're also doing nothing sophisticated. And so we just repeat step by step. And yes, so we hit GTMK time and then spacecraft file. So okay, in real situation, we have to copy that, but it's already here. So filter expression, the same one. So apply cut, no event data file. So we want to, so it needs the input, so basically what it's doing is selecting the intervals when the spacecraft was operating normally. And then, oh yes, I forgot to. All right, let's open up just to give you an idea of how the filtering is done. So yes, so we can open up the filtered file again, and because I forgot to show you something. Okay. So yeah, it contains the, besides the events which were filtered, it also contains GTI, the good time intervals. So these are the intervals of time associated with the selected events. So these are the set of intervals when the selected events were collected. So it's just, yeah, it's very simple, nothing but just a range set of intervals. So from this time to this time. So these are a number of intervals when the selected events were detected. And this is necessary first for exposure calculation and second for running the second step of analysis. So when we run the second step, the GT MK time, we select the intervals with a good quality of data when the spacecraft was operating normally, and these intervals are combined with the ones for the filtered data, and then this is reduced, you know, so you combine these intervals and you get the total, so the intervals where both the selected data was taken and when the spacecraft was operating normally. So this list will be either the same or reduced. So I hope you get the idea, and we go back. So the event data file, so we need to specify the file which I was just opening. So it will take the good time intervals from there. So intervals of the selected data. Let me do that for the first bin. So we need this bin filtered bin 1 GTI. All right, and then output file. So we'll just take the previous name and add version 2, just to not override this again. Bin filtered, and we are doing it for bin 1. For first energy bin, and so it's done. So we, was it done? Yes. Let me see. Yep. Should be good. Let me check. Yes, version 2. So yeah. So this is the output file. So where we have the events were filtered through the second filter. So operation of the spacecraft was good, and okay, we can open up and see. Let me check. So again, so these new GTIs is the combination of the normal operation of spacecraft and the events which were selected according to our criteria. So we have the same number of events, right? So we can make a conclusion that during our time range of interest, we didn't have any anomalies with the spacecraft. So yeah, we're lucky. But okay, if there was something wrong with the spacecraft, it would cut out the time intervals where we had problems with the spacecraft. So again, these are filtered events which match our criteria and where the spacecraft was operating normally. So good. So I won't rerun it for all 3 bins, as I already did that. So the output files are here. So Markarian 501 bin fill. So the naming convention is just, I'm giving the names and just to differentiate, you see, so to understand what is the output, to which step the output was created. So GTI, so it means after the good time intervals were identified. So, and for first energy bin, second and third. So this is the output of this step. So now we have all the filtered events, which can be used for our analysis finally. And there is a useful command which is named GTV-cut. So this is basically the summary of all our information of all the cuts applied. So if you run, for instance, you have to run it over the filtered files. So you run this command and the name of the file you want to check which cuts were applied. So if you're confused, if you don't remember, if you have several different selections performed, for instance, you made one selection, you see that you have very few events. You have to you obviously see you applied too tight constraints. Then you want to loosen your cuts, and then you have several versions of your selections of data. So you want to distinguish. If you're confused with the names, you can always run this command and check what criteria were applied to filter your data. So apply it to these filter GTI, for instance, bin 1. They're the same for all bins. So, and extension name events, okay. So it provides you the summary of all the cuts applied. So position, so it was selected from the circle with this center, Ra and deck, and the 10-degree radius. So GTI is suppressed, so you use the good time intervals, bit mask. So event type 3, the response functions, the energy from 100 to 1000. So you remember, okay, you see, okay, this is the events for the first bin, so from 100 to 1000 MeV, and the zenith angle 0.90. So, and you can check if you need to check anything with this tool, you can do that for the cuts. Then we want to proceed to next step. So make counts map from the event data. So at this step, we will be binning events in space. So you remember in the file we opened, the filtered file, there was, okay, many rows, and one of the columns, it was Ra and deck. So the arrival direction of the photon. So we can bin that in, we can create a pixel map and just bin these photons in space, so over the two-dimensional grid, and this will produce the image of the source. So this will be the image in 3 different bins when we will run this. So it will be done using the tool GTBin, which is used with the function CMap, which is binning it in space. So we just repeat what's written here. So GTBin is the tool making the binning, in particular maps, GTBin, and we just run it simply. And then we want to run it with the option CMap to get the images, CMap. Then we need to specify the event file. So binned, filtered after 2 steps of filtering. The final filtered files, which are this one, filtered GTI, and bin 1. We will do that for the first energy bin. The output, we have to give name to the output file. So for instance, Markarian 501 CMap, as it will be the second version, to not overwrite, so I will add version 2 CMap, and bin 1 fits. So this will be the output file where our maps will be located. Then the spacecraft file, okay, it already knows the spacecraft. So now we need to understand how much pixels we want. So a typical value of the image scale is 0.2. So 1 pixel is, so if you will have too many pixels, you risk to have noisy images, because you will have 1, 2 events in each pixels. It will be mass. At the same time, you don't want too few pixels, because you will have barely any resolution. So you have to have good compromise for the number of pixels and the number of photons. So the standard image scale is 0.2 degrees per pixel. So 1 pixel is 0.2 degrees on the sky. And starting from this value, you can calculate how much you want number of pixels. So I applied, so here in this tutorial, they used, I think 15 degree, yes, 15 degree radius. So that's 30 degree diameter and divided by 0.2. That will give you 150 by 150. So I applied 10 degrees, slightly tighter region of interest. So 10 degrees, which is 20 degrees diameter, so you divide this diameter of your region of interest per the scale and you get, so 20 degrees by 0.2, which is 100 pixels, right? And so you type here 100. And so again, 100. And the same for y-axis. So 0.2 is the recommended image scale. Then coordinate system, you just select default values, celestial. Then you need to specify the first coordinate. So you need to specify the coordinates of the source. You can find them either in Simbad, for instance. So here, or when you were selecting your data, so you specified Markarian 501. So you have your coordinates here as well. So it's up to you. You can just copy from here. So, but okay, I already have them in the memory. So, but if you run it for the first time, then you need to really to copy those here. Just do like these, you know, copy and paste here. You see, so like this, your source will be in the center of the image. And so rotation angle, so how much you want to, if you want a slanted map, so but we really don't want to, we don't really, it's for orientation purposes, so but we don't care. So we go with 0. And the projection method, so the projection method, so you just do whatever standard is, so AIT, so, and you, sorry, yeah, I lost the window. So yes, so AIT was the standard recommended. So now you have your maps generated. So I did it for all 3 bins. And so we can now open them and look at the images. So we use DS9 to load FITS images and see what's inside. So the C maps, so I did it for 3 bins. So we won't just repeat the same all over for 2 bins more, bin 2 and bin 3. So we just load them with DS9. So DS9 Markarian 501 C map for the first energy bin and bin 1. So bin 1 is the map from 100 MeV to 1 GeV. And okay, this ampersand allows you to work in command line while loading the software. So you see, I don't disrupt my command line. So this is the image, and okay, honestly, it looks very dull. Okay, can you see something here? Yeah, it's just boring. So we want to add some color. So typical what is used for gamma ray data. So the B, so color B. And you can play with scale. We will, for this, we won't really apply typically. So square root scale is applied. So, but it looks way too, you know, way too noisy. So because we have pollution. So in this energy range, 100 MeV, 1 GeV, low energies, we have high contribution from the galactic background. So I can remind you, so this guy here, yes, so this is contributing it at very low energy range, so around 100 MeV. So to remind, this is where cosmic ray protons are colliding with the interstellar medium protons. So we have gamma rays around 100 MeV. So this noise is actually stretching up to, I don't know, galactic longitude 20, 30. Anyway, so the source is located at around 38. Okay, I don't remember the galactic latitude of the source, but clearly you can see that there is strong background contribution. So probably you remove at the moment, so you apply linear scale so we can better see the details. But if you don't have background contribution, we can apply that to enhance the details. And okay, it looks very, again, still it looks a bit dull. We want to make it smoother. You see there are black dots. So we want to apply certain smoothing. So to do that, you press analysis, smooth parameters, and then you select you select Gaussian, so it will convolve the image with the Gaussian. So you will basically, it's like a Gaussian blur. So you want to select the radius. So the more is the radius, the stronger is the blurring. So let's go with standard 3 sigma blurring. And so this is how it looks like after smoothing was performed. So this is our source in the very center. And here we have all the rest is background. And at low energies, we have very poor PSF, so very bad angular resolution. So you can see that the source is actually stretching for many pixels, and all these dots, all this stuff, all this blue, and this is all background contribution and background, unresolved background sources. So you want to model that with, you see why, so why you want to model the background thoroughly. And aperture photometry is not that good for that because you have very inhomogeneous background. And with likelihood approach, you can thoroughly model all these features here. And so that you will analyze purely the source region and have accurate modeling of the background and the source. Good. So now we can open the second bin map. So it was for low energy bin, so 100 MeV, 1 GeV. Now we load the second one. So 1 GeV, 10 GeV, so at higher energies. So again, we add color. And here you see it's very dim. So we want to add probably scale obscurity to enhance a bit. And yeah, it still looks not so great. So we want to smooth a bit with the same kernel, and it looks much nicer. So you see your source in the center. You have a couple of background sources and the contribution from the galactic background and isotropic background. And so this is for the second energy bin, and the highest energy bin, bin 3, 1000 GeV. We open up the map, and so we see how it looks like. We apply the same, so scale SQRT. We want again to do some smoothing. Maybe we do stronger smoothing this time. So yeah, you can see that there is virtually no background now, as at around several tenths of GeV, you barely have background noise. You have only isotropic diffuse background, and the point sources that you don't see anything other point sources which can contribute. You have mostly purely your source Markarian 501. So this is point source, so it's not that interesting. The maps don't look that exciting, but you need to have a look at the maps even for the point sources to identify that you have applied proper cuts. You don't have anything weird artifacts in your region of interest. So it all looks good. So we can continue. We can run the next steps. And yeah, again, if you have any questions, you're welcome to ask. So next we have to produce the bin counts maps. So essentially it will repeat the same. If you want to apply finer energy binning, it's good to do it at this step. But as we see, we have not so much events. So we just stick to the same binning. So essentially, we will proceed with the same 3 bins. So each bin is 1 decade in energy. So this is this counts cube, which in my slides was, so yeah, this is counts cube. So if you want to bin it more, fine, but we will stick to the same binning. So to run, I will run an example of the counts cube. So why cube? Because okay, one map is 2-dimensional, but if you bin in energy, you add another dimension, so you have a sort of like a cube. So you run gtbin again, but now with the option c cube, counts cube. Let's do it quickly. So you see gtbin c cube, and then it will ask you for input. So gtbin, then you want the algorithm c cube, and then you need to specify the filtered event file. It will process it and extract the events and bin them in energy and in space, both. So this is the bin filtered GTI. Yes, it already remembers. So yes, so the output file name, you can name it, for instance, Markarian 501 version 2, to not override what I was creating yesterday. So C cube, because we are running C cube, and then okay, bin 1 fits. And spacecraft, okay, it's already in the memory. So if you want to, if you agree to what it is proposing, you do nothing, you just hit enter. If it's wrong, then you just specify whatever you need. Okay, so number of pixels. So it will be the same number of pixels, you see. So, but you have to be careful, because in fact, the number of pixels is, so you want a cube for, you see, so for the acceptance cone, so it's a square which is encircled. So you want, it will be not exact, so the diagonal will be equal to radius, but the size of this square will be the acceptance cone by sqrt, so square root of 2. So this is because the binning is, so you do a square binning from this circled region of interest. So you are cutting a square from the circle, and so you have to be aware of the fact that you have to remember to multiply the result by square root of 2. So in their case, so they were binning 150, and now they're binning with 100 approximately. We have not 15 degrees, but we have 10 degrees, so we have to specify other values. So let me compute that. So roughly, okay, let's do it with Python. So I have to import NumPy for sqrt, or I will just run the, so I have 10 degrees region of interest, right? But the diameter will be factor 2, 20, and the okay, no, the, okay, we can just directly multiply by the radius by sqrt of 2, so 2 to the power of 0.5. So this, the size of the square will be, the side of the square will be 14 degrees, okay? And we are curious what's the size in pixels. So we have to divide this value by image scale. So pixels, sorry, degrees by degrees per pixel. Degrees per pixel is 0.2. So it's roughly 70. We will round up to 70. So we will have 70 pixels. Oh, yes. So we have 10 degree radius region of interest, and then the square and squared, whatever it is, it has size of, so it was 100 pixels, right? And we have set only 70 pixels because it's smaller. So we say 70 pixels. So The same for y-axis, 70 pixels, 0.2 scale. So we keep scale the same, and we agree. So it's offer it. Well, this is the standard. Like the standard. So coordinate system celestial. So we enter the standard value. Celestial, we agree. Then the coordinates, we have to specify the coordinates of Markarian 501. So the same as here, so it already remembers. Rotation 0, projection method. So if you're unsure, you check here. So AIT, offering AIT, so we agree. So energy bins. So if you want to do finer energy bins, you specify the algorithm, the log, for instance, and then the starting and ending energy. Okay, in our case, we will not do any fine binning. We will stick to the same one, and we will specify log, and then the start value. So this is the first energy bin. So it starts with 100 MeV and stops at 1000 MeV. And okay, if you want finer binning, you can specify 2, 5, but we will stick to the same binning, so we will have only one bin. We keep it the same. And so now it's done. So we have our file. We have our file version 2 C-cube. So, and we can open it. In fact, I did it for all 3 energy bins. So this is here, C-cube, bin 1, bin 2, bin 3. Again, to not rerun. So we can open them up, and it will be the same counts maps. So if, for instance, if I take the C-cube, if I would apply finer energy binning, there will be like a stack of images. But since I stick to the same binning, it will do nothing but display the same count map. So you can verify it here. Okay, so just the same scale, SQRT, color B, and to apply some smoothing analysis, smooth parameters. So yeah, you see it's the same thing as was before. So, but if there will be finer binning, you will see several images, how the image progressing with the energy. Cool. Now we proceed to the next step. So we want to, we need to download the latest diffuse model files. So yes, so yeah. So where do you get it from? I think in the lectures I gave the link. It was somewhere in the first step. So yeah, so you click here and you access this page. And so the what is on top is the latest. So you need to download this file. We won't download, I already downloaded it, so it weighs 400 megabytes. So we won't do that now. And you need also a response functions, sorry, isotropic. So this will be the model for galactic background. For galactic, the galactic diffuse background, and this will be modeling the isotropic background. So arising due to unresolved cosmic rays, sorry, misclassified cosmic rays, and arising due to unresolved distant lasers and other gamma ray sources. So you want to download this stuff. So this will be two background models which are ready to use. So, okay, this is already done and I have them downloaded. Then next step would be, yeah, so we need to create the XML model of the source. So if you remember, yes. So it contains the description of the model of the composite source. So I showed you the counts maps. So you saw there was background, there was source, there was a couple of other point sources possibly. So you want to include, you want to specify the description of all of that in a sort of a file like this, where you describe your sources and you describe your best guess parameters. So, and let me open a file. So, okay, you have two choices how to generate this file. So there is an example of this file. You can just click here and it will be the XML file for 3C279. So they have tons of sources here with many parameters. I don't imagine how they fit anything with that, but okay, since they fix parameters, it could be fine. But yeah, so you see there are many sources and they start with the main source. So okay, they have it alphabetical. Anyway, so this is an example of the XML, and you can just copy from here and modify it for your own needs. Another choice is to generate it with the script. So they offer you to use this script. So everything is in this description. So you can open it up here, and so user contributions is the convenient tools introduced by users. So you download this file. So this is the script that may generate the XML file for you based on the specified parameters. So we won't do this. It's doing automatically, but what I did, I just used the XML file they provided, you see, and just modified it to my case. So let me open it up and we can see what's inside. I named it Markarian 501 model XML. Okay, we are actually not far from the end. So this is the just standard lines, so header, and now every source is separately. It starts with source, so the source description starts with source and ends with /source, like HTML syntaxes. And we have three sources here: Markarian 501, so galactic diffuse background, and isotropic background. So I didn't include any other point sources for the sake of simplicity, and the contribution from the sources is low over the 1 month interval. But if we see that the analysis, that the values of the fit are not satisfactory, we can always complexify the model. So you see, we start with the simplest model. So one source, which we are analyzing, plus two backgrounds, this is it. And then we can add next sources. If you remember, in the first counts map, there was some weird point source near the 501. So we want to model that if we don't see it in the model generated counts maps. So we will check it out. So this is the most simple model, and it is coded in this way. So what each source has, let me walk through the parameters. So for each source, you have specific attributes. So you have two branches, so spectrum and spatial model. So spectral and spatial model. So for spectrum, this is the part for spectrum, so 501. So let's assume the source has just simple power law spectrum. So the description of these models can be found here. So for instance, if you want to specify power law, so again, this is Fermi website. So, and if you dig in here, you can find it somewhere, or maybe even the links are, yeah, description of available, so generating source model. So clicking these links, you will access what I'm going to show you now. So power law, broken power law 2. So these are templates for different spectral models which you can use in your analysis, exponential, cutoff. And how do they look like? So this is the second link. So spectral models, so the units are centimeter minus 2 seconds MeV per MeV for point sources, and for diffuse you have steradian minus first in addition. So this power law is this template is defining this function. So N0 is prefactor. I don't know, maybe I can do it more conveniently. so we can see both at the same time. Let me try. Okay. Cool. So power law is this. So you have N0 prefactor. So this is here. So prefactor N0, and I allow it to vary. So free equal to 1 means yes, it is free. It can be varied during the optimization. So, and I set value to 1. I set the scale 10 to minus 10. It's a standard flux scale for this type of source. I'm guessing it. And then I allow it to vary in the range from 10 to minus 4 to 10 to 4. So the total range of prefactor variations will be 10 to minus 14 to 10 to 6, as you can see. So this will vary this. Then index is the gamma, so slope of our power law. So I set it to minus 2. So I assume the shape is minus 2 in the narrow bin. And when I set minus 2, when I integrate it, you can get the physical flux measurement. So if you do wide energy binning, you have to specify minus 2 and fix the slope. And then you will have a measurement of physical flux in the energy bin. So you free equal to 0 means fixed parameter. You don't vary it. So these values will be ignored. It will not do anything. It will just set this value to minus 2. And then the scale is, don't confuse with this scale. So this is the scale of the parameter, and this scale with the majuscule is in fact E0. So here it's set as 100 MeV and it is fixed. So E divided by 100 MeV. In this case, the prefactor, irrelevant of the slope, it will show you the flux at 100 MeV. If you want to compute flux at higher energies, you just use this formula. So 1 GeV divided by 100 MeV will be 10 to the power of minus 2. So you multiply prefactor per 10 to minus 2 and you get your flux measurement at 1 GeV. But this is when we will find out the prefactor. So the likelihood will do the optimization and find out the prefactor so that the data is the most probable. And so the spatial model is just point source, nothing interesting. So you specify raw and dec. So these are coordinates of the source. Then for the galactic background, so this is a diffuse source. So you explicitly write diffuse source. Again, so this was taken from the example. So this was already coded. So you just use as it is. So this is like a standard template. So the spectrum is in fact power law, but with 0 slope. So you assume it's just a template with some floating constant, and the constant can be varying from 0 to 10. So it's free. So, and these parameters are fixed. And so 0 slope means you have constant value. And the spatial model, so you remember we downloaded this file. Okay, yeah, so we downloaded this file. And so we are specifying the path to this spatial model of galactic background. So, I mean, if you're curious, we can even open it up. Fits viewer, no, DS9, GLL, IM. So it's a very heavy file, 400 megabytes. So, and so you see, so cube allows you to select the size, the energy at which you want to. So you see, when we go higher in energy, the contribution of the background is decreasing. But at low energies, so we select at low energies, and then we want to apply scale, skewer T, for instance, to highlight the details. color B. So this is the model of the background all over the sky. Probably some smoothing, I don't know, with a very small kernel. Oh yes, it's a very heavy file, so I regret that I did this, but okay, because it takes some time. Okay, now it's done. So you see you have very polluted region near the galaxy plane, and still you have some contribution even far away from the plane. You have some, you see some features. So this is the template, the spatial template used to model this background, the galactic background. And the isotropic background is, maybe I will open up. So this is the downloaded template for the isotropic background. So this just, okay, this is a plain text file. So it just shows the spectrum of these, it just shows the spectrum depending on the energy. Nothing to see here. So yeah, so we specify the path to the spatial template, and we allow it to have some coefficient, because we know the model approximately order of magnitude, but we allow some adjustment to the real data. And so isotropic background is the second background and the last source. So I specify the path to this text file. So this is the spectrum, and I'll allow it to have varying normalization from 0.01 to 10. And the spatial model is just the homogeneous constant value. So this is it. So this is our model. So to sum up, so we have our source of interest, point source Markarian 501. With this spectrum, we have galactic diffuse background model with the template, which I just showed you, with varying adjusting normalization, an isotropic background with the spectrum, with this specified in the file, again with the floating normalization. And this is it. So this should be able to fit our data. And the likelihood optimization will, in fact, vary 3 parameters. So this one, 3 equal to 1, right? So the prefactor in the spectrum to get the physical flux measurement in the bin, galactic diffuse background normalization to adapt, and the isotropic background to adapt to real conditions. So only 3 parameters. We are mostly interested in the prefactor because this is the measurement of the flux in the energy bin number 1, number 2, and number 3. So this is it for the model, and we're almost ready to run the main tool, so DT-like. So, but first we need to compute, where is the tutorial? Yes, we need to compute lifetimes and exposure map and the source maps. So lifetimes and exposure. So we need to summarize, like to compute how long we were observing our source, right? So you remember the GTIs. So these were intervals where both spacecraft was operating in normal regime, and we were detecting our events which satisfied the selection criteria. So if you like stack these GTIs, you will have your total lifetime. But your effective area also depends on the response of the detector, because depending on the orientation of the spacecraft with respect to the events and depending on the energy, your response of the detector can be different. What I mean by response is that, for instance, if you had 10 photons from the source which were falling on the detector surface, it doesn't mean necessarily that you will get 10 counts, like you will have 10 trigger events in your detector. Due to the different response of the detector depending on energy, you may detect, for instance, only 2 events or 3 events, or I don't know, 9 events, depending on the energy. The same as with your eye, it's not sensitive in the UV or in the infrared, so you get 0 counts or very few counts near the violet or red part of the spectrum. The same with the detector, or the same with the when you're trying to see the what's behind you get zero counts. So the same I mean by the response of the detector, but in gamma rays. So you don't see certain, in some energies, your detection capabilities are very limited. So you need to take that into account. So you generate the so-called lifetime cube. So this creates a cube of lifetimes. So the integrated lifetime, which is depending on the inclination of the spacecraft, depending on with respect to the z-axis, and let me recall. Yes, so yeah, off-axis angle. So yeah, number of counts depends on lifetime, obviously, and off-axis angle. So it computes depending on, yes, sky position and the off-axis angle. And this is needed to speed up the calculation of your model counts. So when you will compute the model map, so how the source would look like if your model was as it was assumed. So you need to compute the model counts, so predicted counts. You need to know the exposure, right? You need to know how long we were observing source, and we need to know the response functions integrated into that. So we need to pre-compute it for each possible value of sky position and off-axis angle within our range of interest. So we run these GTLT cube according to the manual. So just using Zmax equal to the value which were selected first, Zmax 90. Let me do this. So GTLT cube Zmax equal 90. So it's asking for the event data file. So they filtered. So yes, for this one, but for instance, for first energy bin. So spacecraft, okay, it's already in the memory. Output file, so we give name to the output file, let's say LT cube bin 1, but so version 2, to not overwrite which I created already. So version 2, LT cube. And for the first energy bin, so for the step of the cosine theta, we use the standard values. So you see cosine theta 0.025, pixel size 1. So we use standard values provided in the manual. So now it's generating you the lifetime cube. So it takes a while. So for large, very large observational so here it will complete in 1 minute, I guess, or 1 minute and a half. Or when I was analyzing the large Magellanic Cloud data stacked over 10 years, so this calculation was around 3 or 4 hours. So you can imagine, so this is the most time consuming step over all of this analysis procedure. So yeah, meanwhile, we can look into the next step, which we will be doing. So we need to compute the exposure, so which is the convolved, let's say the effective area convolved with the observational time, or more like, so it's measured centimeter square per second. So it's multiplication of the effective area by the observational lifetime, and the taking into account the response functions, so that if you divide your counts by the exposure, you get physical flux in photons per centimeter square per second. So you will just compute the exposure starting from the output of this tool, which is now being calculated. So yes, it's showing you the progress. So we'll be completing soon, and we can have a look on what's inside, probably, or maybe no. Yeah, maybe it's not so interesting. So we're 3 steps ahead, 3 steps before the running the likelihood analysis, where we can see something. Okay, we just wait for this step to complete. Okay. Okay, XML. Yeah. Yeah, and then after we computed the exposure, so the effective area multiplied with the lifetime, so we can compute the source map. So what is source map? So these are predicted counts. So we had an XML model file with all the components specified. So these observational times will be applied to the model. So what will be done? So the XML model, so our model of the source will be multiplied by the exposure, which we'll calculate here, and then convolved with the instrument response functions. So it will simulate the response of the detector, and so we will simulate the observational data from the model which we specified, and then we can compare to the real data to find if our model is satisfactory. And also it will be used as an input for likelihood analysis. So when we will find the model parameters so that we match the data closely, so we find the parameters which maximize the probability of the data. Good. So I think our analysis should be yes. So it's ready. So we ran the LT cube, the lifetime cube. So now from that we need to compute the exposure. So it's just GTX cube 2, right? The name of the tool. We do it here. So we type and it wants the lifetime cube that we just created. So this guy here, then the counts map. So okay, so we want to, so the trick here is that due to the low quality of, let's say, the instrument response functions are very poor at low energy. So you have very bad angular resolution. So you have contribution to your source from the sources even outside of your region of interest. So you need to take that into account, and you need to compute your exposure for wider field of view than I was showing. And it's simpler to just compute the exposure map for the entire sky to have it handy. And yes, so in the manual, so this is how you do it. So this is the example for wider field of view, and this is for the entire sky, which they recommend and I also recommend. So here the entire sky is 360 by 180. Okay, with the image scale of 0.2 degrees, this converts to 1,800 pixels per 900 pixels. So you just compute your exposure for all the sky, and this will be convenient because you will not have to think to recalculate something. So we have a ready, and it's not that longer than for just wider field of view. So you run it like this. So you just repeat whatever is written here, because it's a standard calculation for the entire sky. So there is nothing different from our case. So you don't need any counts map known. So output file name, for instance, Markarian 501 version 2 all sky, as we are computing for the entire sky. So exposure cube bin 1 fits. So yes, response functions. So we are using the, you see the spectral template for isotropic background with the response functions P8R3 source V3. So we're good. So they recommend us to use, so in order to, when you applied the cut on the source, on the on the event type equal to 3, so included front conversion and back conversion, and for that you need to use these response functions to have self-consistent analysis. So P8 R3, so the latest response functions, and we're just checking that, okay, the yes, sorry, so we're using the proper template, so with the same, calculated for the same response functions. So you need to have self-consistent analysis. So you use these response functions. So the name, you copy it, and you use all the names the same as here. And one, yes, 180, 900. So all sky, 0.2, first coordinate. So you want your source in the center. So the coordinates are already there. No rotation. So projection method, again, standard coordinate system, and start energy. Okay, since you're in the first bin, so it's 100 MeV, stop energy is 1000 MeV. So for the second bin, it will be different values. For third bin, and number of bins, okay, one bin, we want only one bin. So it's computing the exposure map, generating it from the lifetimes you just computed. So it's taking your lifetimes and taking into account the response functions and computing the exposure. So how long you were observing multiplied by the effective area. So, and I did that already for second and third bin yesterday. So we can open up and check quickly. So exposure maps, yeah, all sky exposure cube bin 1, for instance. So if we open it up, okay, it will be just a table with exposure values. So GTIs, they're just copied from file to file to have them. So energies, and so this is our exposure map. So yes, okay. So the animation, so this is the exposure map depending on the sky position and the inclination angle. So okay, just showing you the exposure map for the entire sky. Maybe we can check it in DS9 as well. Maybe it will be any better. Yeah, probably better. So yeah, it depends on the energy, and we want to select. So we have one bin, so we can just take first slice, and yeah, so maybe we can color it up, and maybe no scale, it doesn't make any sense. So the exposure depending on the, or for the entire sky. So you really, I mean, it's just for demonstration purposes. So just so that you see how these files look like, what's inside. And so now we're done with the exposure, and we can do the last two steps of our analysis, and we will be done for today. So very quickly, so we compute the source maps. As I said, we compute the predicted counts. So so you see this exposure map. So it convolves the model with the exposure, multiplies, sorry, the XML model by the exposure. So you remember we put there the assumed physical flux. So when multiplying by exposure, it will get you the number of photons. And when convolved with IREFs, it will give you the number of counts. So you will have at the end of the number of counts depending on the sky position. So this will generate you the predicted observations from our model that we have chosen. So for that, we run these tool GT source maps and specify the input. So you see that each tool, it requires as an input some files that you have, that were the output of the previous steps. So it's like a pipeline. So you can copy the names, and yeah, it will work as a pipeline. So you put the name of the tool, you invoke GT source maps. So you need the hypercube, so the LT cube file. So what was the file? So it was version 2 LT cube bin1. You need the counts maps, so the counts cube, in fact, depending on energy. So C cube, version 2 C cube. You need the source model file because it will use your model to predict counts. So Markarian 501 model XML. So the scripted model with the description of the sources. Then you need the exposure map, which we were just looking at. So all sky exposure cube. Good. And then the name of the output file. So we will choose Markarian 501 version 2. Okay. Source maps bin1 fits. We're good. And then response functions. So which functions to use? So the standard ones, KLDB. So you do nothing, you press enter. And now it's generating you the source maps, and we will be able to look at them in 1 minute, I hope. So it's creating the predicted counts map, okay? And we can look it up. And I did it for, we won't repeat for second bin and third bin. I already calculated yesterday. So these are the source maps. So we can check DS9 because we want to see image. And for instance, for the first energy bin, so this is the predicted counts map for our model, what the observation would look like. So again, we see, okay, it's very dirty, so we don't apply the scale, we choose linear scale, and then we smooth it up with the analysis. Smooth parameters 3. Okay, so this was the counts map. So this is the predicted counts map from our model. You see, so we have our source, we have our background, and we want to compare it to the real data. Let me do that. So GS9, we need to specify the CMAP bin1. And we've got, so this is the model predicted, and this is the real data. So scale, we don't apply scale, okay, color B, smoothing with the same kernel, smooth parameters, 3, apply. So looks pretty, where is it? Okay. Okay, I lost it. Ooh, sorry. Did I just close it? Okay, I have to reopen it. So CMAP. Okay, really sorry. I don't know what did I do. So color B, analysis, smooth parameters, apply. Yeah. So yeah, so this is the model predicted, and this is the real data. So you can see, okay, this looks fairly similar, right? So you can see, okay, different, okay, it looks, it's squared cut from this, but otherwise you have your source, and it has the same shape more or less as the real data. Why? Because you included your response functions, so it's actually simulating how your point source would be looking blurred in your real data. So you have similar maps, so your model is okay. So you can continue with the analysis and run the final step. So the final step is GT-like, and that will be it for today. So what does it do? It actually running the optimization of the parameters in the XML file. and tries to match the model to the data. And in more detail, so as I discussed, this tool is actually optimizes the parameters which are allowed to vary to maximize the likelihood function, so that for the model that we adopted in our XML file, the observed counts, the observed data appears to be having the highest probability. So we have the highest probability to obtain your data from this model. So you will have the maximum likelihood, so the most likely values of the parameters to produce your data, to have your data be produced under assumed model. And these values can be used to obtain physical flux measurement. So you remember prefactor is actually defining the physical flux. So let me run, so GT-like, we need to do things according to the manual. So I don't want to apply any refit because it's a simple model. We have nothing really over complicated here. So we apply refit no. We don't want to refit. We don't really want to plot anything. So, and the S file is the output file where your optimized parameters will appear. So you have to give some name. So GT-like. So the final step, so we want to apply bind statistics is here. So bind, and then all the files which you were generating before. So this will be the input. So this is the final step. So counts map. So you need to specify source maps where you have all your information, model counts, and the data. So this file, the last one, which we just produced. So we want bind exposure map. So again, so this is the all sky map of exposure which we generated. Yeah. And then we want exposure hypercube, so LT cube. So all the stuff from previous steps, it wants it to include in the analysis, and the model, of course. So because it will use it to optimize, and the name of the model is here. So XML file, we have only one XML file, and the response functions, so we just use the standard ones, and the optimizer new minuit, so all standard values. And now the likelihood analysis will be running. So it says that minuit did, so minuit is the name of the optimizer, which is fitting, which is performing the fitting. So it did successfully converge. So the likelihood value will be displayed. So, okay, this is covariance matrix for the errors. So a lot of interesting information, okay. Some auxiliary, yeah. So you have the output values here and also in the output file, okay. So galactic diffuse background. So you have your prefactor, which was fitting. So prefactor with the error flux. So this is flux. So it's giving you output in flux per photons per centimeter square per second. So isotropic background, and the Markarian 501, our source of interest. So prefactor, index scale. So TS is test statistics. So this is some statistics this will be needed for if you do something more sophisticated. Okay, comparing different models between themselves. So you want to know this value to know which model is most likely. But here we won't do anything like this. So value the minus log of the likelihood function, and it took 9 seconds to compute that. Okay, so this is the result, and so your flux from Markarian 501 in the first bin, so from 100 MeV to 1 GeV is 1.1 plus minus 1.9, so 1.1 photons per centimeter square per second with this scale. So 1.1 10 to minus 7 plus minus 0.1 10 to minus 7 photons per, and if you repeat that for other two energy bins, then you get your spectrum. So you will get 3 spectral points. So we can repeat. So I already did that, and we can actually just repeat all of that again for all of the energy bins, or we can use the values from the output files. So you see, so this is the output XML files after I ran the likelihood analysis. So you can check, for instance, I don't know, you can just open it up here. So it's the XML model file after the likelihood was run. So this is the values which were fitted. So this is the value of the prefactor, the error, and so the optimized to have the highest probability of the data. So we're not really interested into these values, but we just check that they're reasonable. If, for instance, they are falling to the close to the minimum value or maximum value, or you have some trash there, I don't know, something weird, then you have to check your model, you have to do something, but we have all nice here, it's nothing suspicious. So our model is good and we can trust these values. And so let me calculate. So we were using this formula to estimate the flux from the source using, so as this is our model. So we have our prefactor 0.86, right? And we have to multiply it by scale equal to, sorry, I'm doing the wrong, yes, we need the Markarian 501 prefactor, I'm sorry. So value is 12. We multiply it by its scale, 10 to minus 10, yeah. So, and then we have to specify the, so power law minus 2 with the 100 MeV scale, and we are computing in the energy bin from 100 to 1000 MeV, and the associated median, so let's say energy associated with this bin will be square root of the 2. So it will be 100 by 1000. So it will be something like 300 MeV. And this should give you the measurement of the physical flux. So it will be 1.22 10 to minus 1.22 10 to minus 10 photons per centimeter square per MeV. And I think, okay, we had, yeah, so it is, I'm missing 2 orders of magnitude, I think, because it says 1 10 to minus photons. Yes. So this is per MeV, and this is per, yeah, we have to multiply by the, also I forgot, we have to multiply by the bin width, because this is per MeV. So we have to multiply by 900, so 1000 MeV minus 100 MeV. So yeah, we get the value that was computed in the likelihood, right? So you get the idea. You can either extract the values from the likelihood output, maybe that will be simpler, or you can, if you lost, for instance, if you close this window now, you will lose all your output. You can output it to file, of course, but if you didn't do that, you can always access your flux from the optimized output XML. So let's quickly just plot the spectrum, and for today we will be done. So we have to, so this is the first physical flux, right? So we will compute, I won't rerun GT-like, I will just estimate the fluxes for other bins from the XML file, and then we plot this thing, and yeah, we will be done. So for bin 2, and I already do that for bin 3, And so I again access Python and I recalculate. So maybe I can create a file with the spectrum one 501 spectrum spectrum txt, and yeah, so I will save my spectrum to this file. Okay, we need the first point. Yeah, we also need the error bar. Ideally, we want to know the interval in which our value is located. So you see, so okay, I will first put the physical flux, then the energy bin. So 100 MeV, 1000 MeV. So this is the value of the flux, and we need an error on that. So for that, we need to specify the prefactor error, which was in this file up. So bin 1, Markarian 501 prefactor value, and error is here. So we put it here. So it will just compute you the error on the flux, which will be the same as was in the output of GT-like. You can really verify it. So yes, so 10 to minus, yes, it's the same value. So we're doing the right thing. Now, so this is the first spectral point is ready. So 100 MeV, 1000 MeV flux, error on the flux. And we repeat it on for the second bin. So what we've got here, so we need to specify the prefactor for the second bin. So bin 2, Markarian 501, value 15, the prefactor. We have the same scale, we've got different, although we have different bins. So we have 1000 and 10,000, the limiting edges. So the scale is the same, 100 minus 2. So we just apply different energy binning. So it's the second bin, so we have different values. So this is the value and of the flux, and this will be your error. So you have to, well, ideally, I mean, I'm doing it manually with my hands, but in real life, of course, you extract all this information using scripts, so you do it automatically. But okay, I do it manually so that you understand the principle. So we are very close to get the spectrum, and yes, this will be it for today. So 2.10 is the associated error on the prefactor. So this will be the second spectral point. So I put here 1000, 10,000. So this is the energy, and this is the flux, and the error is here. So the error is around order of magnitude lower than the value. So it's rather good. And so the final bin of our spectrum, so we look at the third XML file. So bin 3, Markarian 501, prefactor value. Again, it's multiplied by scale. So, but now we have a different energy of the bin. So we have 10,000 and 100,000, the limiting values. So, and again, 100,000, 10,000. So this will be the associated flux, and the error on this flux is Markarian 501, so 7. So the error is getting bigger because we have fewer photons. So at higher energies, you have poorer quality of spectrum. So, okay. So this is the final bin. So you put here 10,000 MeV and 100 1000 MeV, and then this will be the flux, and this will be the error on the flux. And this is it. And so we have our spectrum. So this is the spectrum of our source. So in wide energy bins, and we want to plot this using, for instance, Python, or maybe more quickly, maybe GNU plot. So yes, our spectrum should be here. Let's sort it by, yes, so marker and from a spectrum. So for instance, GNU plot, and we want to set log scale for X and Y axis, set format X, for instance, like this, same for Y. So we have more or less scientific notation. And so we plot that, plot the, oh, sorry, using, so we need to, so first will be the, so we have 100, so we need, so we have energy bin from 100 to 1000, for instance, MeV. So the medium energy associated with the bin will be square root of the multiplication of the two, so around 300 MeV. So this will be, so I explicitly put that, and then, so this expression shows what versus what. So the energy of the bin, which is square root of the first two columns, then the, sorry, third column, the flux, and the error bar, and I have to say with Y error bars, I think. It's been a while using it, but okay. And then probably color, or we will see what will happen now. We can adjust it. So yes, so this is the spectrum of the source. So let's say it's very narrow, and we want to make it wider. Okay, so we want to say line width 3, point size 3, and let's see what happened. Yeah, so this is our spectrum. So first energy bin, second energy bin, and third energy bin. So you see, it's just a simple power law. And we want to, for instance, maybe we can estimate the slope. So I don't remember exactly how to fit that, but okay, maybe we want also to, the typical representation of the spectrum is E square. So this is in photons per centimeter square per second, but we want to, we want that per MeV first, and then we want also that per multiplied by E square. So for that, we want to divide that by the difference of of the energies. So per MeV, you see what I mean? So this will be per energy. So this was the pure flux, and this will be the differential flux. So the spectral, really the spectrum. So I divide that by the width of the bin. So by the energy interval, and I have to apply the same for the error. I could do that in the file already, by the way, but okay. So this is how the spectrum now looks like. So this is really the differential flux, and so you see it's around 10 to minus 10 at 100 MeV, and then declining to 10 to minus 13 at higher energies at 300 GeV, and we have higher errors here. And maybe we can estimate the slope. Okay, ideally I could fit that, but I don't remember exactly. It might be time consuming if I will refresh that. So I can guess the slope. So I specify the function, for instance, 10 to minus 10 multiplied by energy by 100 or 300 in the power of minus, let's say minus 2. That will be my guess. And I plot that along line color second, for instance, line width 3. And you see, so yes, so it's very close to -2. And for instance, you see it's slightly harder than -2, I guess. So we can specify first I need to scale this up a bit. Yeah, it's now maybe 1.5. So we match the normalization. Okay, it's good enough. And now I have to maybe 1.4, and I can make the slope be a bit harder, -1.9, for instance. So I replot that, and yeah, so it fits well. So we found for the spectrum, we found our analytical description. So let's say more or less this is the prefactor, this is the scale. So these values you adjust, and so the slope of our spectrum is 1.9. So it's describing with the power law 1 minus 1.9. And to build the spectral energy distribution, you can simply so I'll remove the model function. So you need to multiply by e squared. So all you need to do is multiply by this. So squared, it will be without square root. So $1, $2, $1, $2, and the same for the error. $1, $2, and yeah. So this is your spectral energy distribution, and you see, so this is actually going up because the slope was -1.9 and you had +2, so it will be a slope of 0.1. So your spectral energy distribution is actually rising in this energy band. So it's really, yeah, it's in fact it's very hard spectrum, and you can final step which we can do is somehow superimpose that and this. So this was the very high energy. So, and we kind of, yeah, we kind of do this. Okay, we can plot this, maybe more professionally extract these points, and but yeah, more or less this is 100 GeV. This is around 100 GeV. So we kind of, you see the transition, how the composite spectrum would look like. So it's rising here, and yeah, you can see it's indeed rising. So we're doing the right thing. So rising and then decreasing. So this will be the composite spectrum. So yeah, I think this is it for today. I hope it wasn't way too long and you were able to follow. Okay, I can stop sharing the screen. And yeah, if you have any questions, don't hesitate to ask. I see there was something in the chat. Okay, somebody was having trouble to connect. Okay, hopefully this was solved. So do you have any questions or comments? I don't know, if you want to ask something, it's the right moment to do that. Okay, I guess no questions. So if you have any later on, you can always drop them in the WhatsApp group. So okay, good. So this is it for today. Okay, have a good day and see you on Friday. I have to discuss with Natalia what will be the teaching, what we'll be actually teaching, but I will let you know. Okay, thanks for your attention.